Who is yours?
Hello everyone. I'm Mohammed Albezzawy from LVA, and I'm working in the framework of the EcoDrive European project, funded by the European Commission. And I'll be talking today about a resynchronization approach based on a technique called the maximally coherent reference technique. And the work is supervised by Professor Jérôme Anthony and Dr. Quentin. Okay, let's define our problem. For when you have only a small array and you want to reconstruct the whole hologram around your object, or if you want to increase the density of your microphone array if needed. So you can move your array around the object, okay? But when you move your array from a place to another, so you are losing the phase information, okay? And as my friend Roma said, the phase is the sources of all evil, Yeah, I like this, so I quoted this. We can see here, this is a data from experiment. This is a microphone array measurements. This is the magnitude and this is the phase. And I distorted the phase. I splitted the array in two parts, and I shifted the signals in the time domain. And then I showed the results. You can see we have no magnitude and no phase as the original signal. Okay, so that's because if we propose a constant source level, so the contribution also can be proposed to be constant. So what it changes from this position to this position in time is the noise term. It's no longer the same. Okay, if X is the coherent part coming from the sources of interest. Okay, and we found that this problem is totally equivalent to the source extraction or source separation problem. Okay, we now considering only one position. Okay, and in this position, this is a simulation, because to show the source separation problem, I simulated here this one source here in the middle of the array. This is the magnitude, and again this is the phase. And I added the noise. I just added noise. So what happened? The noise also destroyed both the magnitude and the phase. Again, so more or less they are the same problem. Here, to retrieve this, I want to estimate this part, which is a noise for another instant of time, okay? Other than the instant of time I was measuring. And here, I'm trying to retrieve the coherent part, which is nothing but the coherent part plus zero noise. So they are more or less the same problems, okay? People use the coherence techniques since the 70s, which is coherence techniques is also called the reference techniques, which is they used some fixed sensors. These sensors could be some fixed microphones, fixed in place, they don't move, okay? And also maybe they could be accelerometers or any other type of sensors. And they tried to retrieve the phase in this case. And also in this case, the same, they tried to retrieve the coherent part, okay? It is the same thing. Okay, this is the mathematical formulation. We have our system here, our sources in the form of a matrix. This is the contribution of the sources. So we have X equals H multiplied by S. And for sure, when we measure, we don't measure by the array, we don't measure X, which is a coherent part, which is I'm interested in. But instead, we measure Y, which is X plus the noise term. And actually, our problem is to estimate X as close as possible, X hat as close as possible to X, which is in other words, estimating the noise term, okay? In the resynchronization problem, we're trying to estimate this and in the source extraction problem, we want to get to n equals 0. Okay, so these are the two equivalent problems, and there is this is the least square solution, which is the basic solution, where SYR is the cross-spectral matrix between Y, and on the other side there is the reference matrix, the fixed sensors, we call them the references, which are nothing but a linear combination of the sources of interest, okay, linear combination N, plus also some noise on the references. And we measure those, we compute the cross-spectral matrix between them, and we compute also the cross-spectral matrix of the references, okay, and we can get the estimate G, which is the least square solution. This is the basic classical technique. But this technique has inherent problem, this inversion of the SRR. If your references are so clean, and they're supposed to be, because they are references, they have to carry much information than the array itself, this inversion becomes numerically problematic, okay? So there's an inherent problem comes with the package. So the assumption is that for this to be well conditioned, we have to use a number of references strictly equal to the number of sources, and they have to be uncorrelated between each other, like each reference is correlated to only one source. Yeah, it's so fantasy. But in place of this, in realistic cases, especially the case what I'm dealing with, which is the overdetermined case, when the user tend to use more reference sensors, more than the number of sources, because maybe he's not sure, he wants to capture the stochastic dimension of the field. And in this case, they will be correlated by definition, because they are more than S. Okay? And this will lead to a badly conditioned SRR, cross-spectral matrix, and then problems. The solutions in the literature, there is two main solutions in the literature. The first one is the conditioned spectral analysis. It's called also the partial coherence technique, which is based on the idea of reordering the R signals, the reference signals, on some basis, like causality or whatever. And then they decorrelate these signals from one another to get an equivalent decorrelated set of references. But the first problem with this technique is that this ordering operation lacks a robust criterion for this ordering, okay? And the second problem, if the user tend to use a number of reference sensors higher than the number of real sources, this may lead to singularity of the matrix of interest, SRR, and it will make a numerical problem to evaluate this solution. Then, in the 80s, the researchers proposed some technique to replace this one, which is the virtual coherence technique, which is nothing but principal component analysis or truncated SVD of the reference set. And it has also some limitation, because I don't know if you are familiar with the derivation of the SVD. It proposes that the noises on the signals has to be, the covariance matrix of the noise on the signals has to be proportional to identity. So our reference set has to be spatially wide in terms of the noise, which is not guaranteed. Okay, they are in the same vicinity, we can say. So what happens if this happened? In this case, the first S is the number of sources. Okay, singular values won't be representative to the true sources of interest that produces the field. And in this case, we will see in the results what this will lead to. There is another problem that's very interesting, because it is not mentioned in the literature up to my knowledge, which is when your cross-spectral matrix of the references is well conditioned. It seems good thing, but not, because in this time it's well conditioned due to noise, high levels of noise on them. Okay, so what you will end up with, a gradually decreasing eigenvalues. And when you have a gradually decreasing eigenvalues, we know that PSA is a truncated technique. You need to have you need to have a separation between the noise floor and the important eigenvalues to decide on a threshold. Okay, so you can't do this when the matrix is well conditioned due to noise. Okay, so this is another important challenge, which is not discussed before. So we proposed a solution to deal with all these things, all the reference-related problems. These techniques, we coined it the maximally coherent reference technique. And it's very simple. The idea is to get a linear combination of the measured references, okay? And so as to, this linear combination is maximally correlated to the data on the array. Just remember, we have two sets, the reference sets, the fixed senses, okay? And the array, which is our target. So we want to optimize this reference set so as to be much correlated to the information on the array that we want to get, okay? We can do it recursively, like getting Z1 to get B1, so as to Z1 is much correlated to Y. Then when we get Z1, we decorrelate Z1 from Y, and then get Z2, etc. And we derived that this solution is equivalent to this simple generalized eigenvalue problem, so it can be done not in a recursive, tedious way, okay? Where we have all the terms, except the solution is unique up to a semi-positive matrix, which can be simple as the identity matrix. There is some other options. Another subproblem, which is very important subproblem, which is the estimation of the number of sources. I won't go through this because it's a bit large amount of work, huge amount of work. I'll present it in another time, but we have to estimate the number of sources in a way to truncate the eigenvalues, either using the truncated SVD, the traditional one, or the proposed technique. Let's quickly get to the results. Here is the first simulation. I simulated some Gaussian signals as the microphone signals, and some Gaussian references, some Gaussian sources, and they radiate. And in this figure, the covariance matrix of the references are proportional to identity, so truncated SVD should work. And when I compared, I'm plotting here, I repeated the experiment for different SNR values of the references, and I'm plotting some error value. This simulation, you can plot errors, and we can see my solution in green, truncated SVD in blue, and in red is the least square solution. We can see when the references are very, very clean, so the SRR matrix is badly conditioned, so the least square solution fails. It gives very high error. The truncated SVD solves the problem, very low error. And so as to our method does. And here, when the noise gets high, they all works the same, okay? I introduced correlation between the noises. And in this case, we expect what? We expect the truncated SVD to fail, while our method still gives the least error, as we estimated. I did another simulation with a bit of a spatial dimension. So I simulated one source here, Gaussian signals. This is the magnitude, phase, real, imaginary. I added some noise. I showed this. And this is my solution. You can compare the magnitude and compare the phase retrieval. And this is truncated SVD. It's underestimated the amplitude. And it failed to retrieve the phase also. Okay? As we expected, because I'm truncating after one eigenvalue in my technique and in the truncated SVD. Okay? And here is the least square solution, which is by definition of the least square solution. It tends to give a solution which is closer to Y than X. This is by definition, by mathematical definition. I did a simple laboratory experiment. We have 2 coupled rooms in the basement of LVA. I use this coupled room to separate between, as much as possible, between the noises on the array and the noises on the references, because they should be decorrelated as possible. And there is a plate in between. I put a shaker as a source. You can see here the references, 3 or 4 reference microphone. I use the 3 of them. And on the other side, there is also 2 accelerometers. I will use them as references also. And we have the array here of 18 microphones. This is a schematic. Yeah, let's do the principal component analysis using the truncated SVD, or the SVD, and using our maximally coherent reference technique. This is the principal components against frequency obtained by SVD. This is of the array. Okay, we can see one source here, but not clear in some frequency regions. And there is some also noises here on some microphones. This is not clear enough. And this is the reference, the SVD of the references. We have here 5 references, 3 microphones, and 2 accelerometers. And what we expect a different noises on the accelerometers than different SNRs and the microphones. And this will lead to a problem to truncated SVD. Okay, so truncated SVD expected here 2 sources, while I'm using only 1 source. When I get the principal component using my technique, I think it's clear by visual inspection, there is only 1 source detected, not 2. If I relied on this is so problematic. And by the way, I think this is an easy case. This is an experiment. It's not a real system. Okay? And for sure, I told you that we need to estimate the number of sources. Okay? So there is some statistical techniques we developed, several, to detect the number of sources automatically. Because even if I can see it visually, but it's always nice to have it automatically. So it is here, you can see for the majority of the frequency access, it's well estimated, it's 1. So this is the resynchronization games that I do. Here, this is the measurements. I disrupted the phase. I retrieved the phase using my method very well. Truncated SVD failed to retrieve the phase, and so also the least squared solution. Also on real data, I got some real data from, this is the last thing. This is real data from an electrical motor from Siemens. Okay, and this is the microphone array. And this is the eigenvalues that I showed in the very beginning, which is gradually decreasing, which is problematic to any principal component analysis technique. Where is the threshold? Okay, and I can say our method said something about the number of sources, because they used 11 references. Some of them was accelerometers, accelerations, and some of them was pressures, microphones. So it's also problematic to the traditional technique. And I can say I retrieved some number, estimated number of sources which is less than 11. So I could have said something about the dimension of the field. It's not 11, it's less than this. Yeah, for sure I don't know the number of sources. It's a realistic case, okay? And here I played the same game again. This is the measurements. I split this measurements on the array into 2 sets. I shifted in the time domain, so I distorted the phase relation between microphones. So I got a phase distorted set. We can see here that the splitting in 2 is clear here in the real part. And here is my solution. Retrieves the phase and the amplitude very well. Okay? In conclusion, very important conclusions, that all the challenges that appear while solving the source separation or resynchronization problem comes from the condition number of the cross-spectral matrix of the references. Okay? So if it is bad conditioned, we have some sort of problems. Okay? And if it is well conditioned but due to noise, we have some other sort of problems, okay? And we propose the technique to deal with all related reference problems together, where these references, they don't have to have the same SNR or power, noise power. They can differ in, which that means they can differ freely in type from, they can be different types. And these noises may be intercorrelated also on the references. And we also propose several techniques to select the number of sources, which is a sub-problem. I'd like to acknowledge the European Commission for funding the project. And thank you very much. I'm sorry if I took 2-3 minutes more. I hope it was clear.
Please, if somebody has a question, please. Yes, please.
On your method, you try to eliminate the correlated noise on your references by combining it with the array measurements. And that considers that your references and your array doesn't have a also correlated noise.
Yeah, that's what I used in the experiment. I used 2 rooms.
Yes,
You want to have a perfectly decorrelated noises on both sides, but
in this case, if you applied a single value composition on the sum of references and the array, wouldn't you obtain a similar result?
no. I tried. I can show you. I tried this. Yeah, for the same reasons. What makes SVD fails is the type of noise. It has to be spatially wide, okay? Which means it have the variance of the noises has to have fixed powers, constant powers along the diagonal of the cross-spectral matrix, and also no intercorrelation. Okay? For example, if you're doing your measurement, especially in industry, and you have a source not of interest, so it's noise, okay, for you, and it will contribute to all microphones. Okay, so correlated noise in such situation is guaranteed.
Yes, please.
Is there a prospect of applying this to identify multiple faults?
I think it can be, it's versatile. It can be.
Say your machine has a gear fault and a bearing fault. Can you use this?
Why I'm saying that is versatile? Because actually I'm simulating and even emitting in my experiments a Gaussian noise. So it's versatile, I think. It's not tonal, it's versatile. So it can be applied to whatever system to detect whatever source. I'm not talking about the non-stationary run-ups. I think my colleague Sagar dealt with this problem. It is the same, but in the non-stationary case. Okay. Yeah. Thank you very much for listening.
Maybe one more question or? No, so thank you again, Mohammed. So thank you.